Hi everyone, I'm Ke Jingyin from Hong Kong Baptist University. I'm very happy to share this research work LogPar Logistic PARAFAC2 Factorization for temporal binary data with missing values to you. This is a joint work with my collaborators from Georgia Tech, Emory University, and UIUC. Real-world data are often collected over time, and the irregular tensor is a very useful tool to represent and process such data. An irregular tensor is basically a collection of matrices with varying sizes in one dimension, and it handles the temporal irregularity in the data. For example, we can look at the electronic health records of patients, and the data of each patient can be represented with a matrix where each row represents a clinical visit and each column represents a clinical feature. And put them together, we have a matrix representing the data of a single patient. And by stacking all the matrices of different patients, we can have an irregular tensor that represents all the data for all the patients in one data set. And this irregular tensor have one dimension, the time dimension, that is varying with varying sizes across different subjects. And all the patients are having the same set of clinical features. And other applications of irregular tensors include spatial temporal modeling, recommender systems, and so on. However, in real-world scenarios, we often have missing data, which is in general inevitable. Here, for the binary data, we are often facing the one-class missingness. For example, here the value of ones in this irregular tensor represents the confirmed diagnosis codes assigned by the doctors. For example, in the first visit, this patient had the first diagnosis. However, for the value of zeros, there are two possible cases. The first is that this patient doesn't have this disease, or the diagnosis was not even performed. Then that means we have some sort of missing data here. The issue is we actually do not know where are the missing entries. So that basically means we are dealing with the implicit missingness. And also we only consider the missing ones. That means some ones are probably flipped to zeros, and we have some missings over the zeros, but all ones are truly ones. The low-rank completion has been identified as a principled way to complete partially observed matrix or tensors. The idea is that we first learn a low-rank model over the observed entrance, and then we try to reconstruct the full matrix or tensor where the zero entrance can be recovered by the low-rank model. For example, given a matrix M with missingness, we can solve for its completion by minimizing the nuclear norm of this matrix and with the constraint that the observed entries must match the reconstructions. This can be transformed into an equivalent form where we have the matrix factorization for the low rank part, and we also have the Frobenius norm as regularizations. And similarly, for the irregular tensors, we can also define a PARAFAC2 factorization, where each slice is factorized into three components. The first is a temporal factor specifically for that subject, and the second is a static weighting vector, which is the diagonal of this diagonal matrix. And that's also specific to that subject. And also we have another factor matrix that are shared across different subjects that captures the underlying factors in this data. However, this low-rank completion approach is not directly applicable to the binary data with implicit missing. Because a trivial solution exists, that is a rank 1 matrix with all ones. That means if we just simply output a matrix full of entry ones, then we can perfectly recover all the observed entries. So recently, another method called PU learning was proposed for the matrix completion. The PU learning represents the positive unlabeled learning and was originally proposed for binary classification problem. In one paper published in ICML 2015, they proposed a PU learning for matrix completion formulation, and then it tried to map the positive unlabeled learning from the binary classification task to the binary matrix completion task. This method handles the implicit missingness, however, is non-trivial to be extended to the irregular tensor, and also it suffers severe overfitting. So our problem is, given a temporal binary irregular tensor, we would like to discover its latent factors and also do the completion. So to tackle this problem, we propose a model called Logistic PARAFAC2. So first we introduce our observation model of the data. We assume that there is an underlying tensor which is real valued and non-negative. And then this underlying tensor M, goes through a quantization process to obtain our binary data, which is clean. That assuming we don't have any missing here. So how do we do this quantization? Basically, because this M is non-negative and is real valued, we first define a function which is very similar to the sigmoid function, taking the same shape with the sigmoid function, but is customized for the non-negative input that outputs a probability score. And then this binary data Y takes value of 1 with this probability sigma of M. And finally, we can take a subset of this Y as our observations that accounts for the missingness, where we have a subset omega. Now, what we try to factorize is not those observations, but this underlying tensor. We approximate this underlying tensor M with a PARAFAC2 factorization. If we don't consider any missingness, which means the observation X is equal to the binary clean data Y, then we can define this optimization problem to solve for this US and V based on this observation model. First, we have this UK, SK, and V. We multiply them and go through this quantization process to get this reconstruction XK hat. And then we compute its negative log likelihood of this observation model as the objective function. However, this method doesn't consider any missingness, and as we said, the one-class missingness is basically inevitable in real-world scenario. So what we try to do here is to extend this NNPU learning, which was originally developed for the binary classification problem, to the PARAFAC2 model. This is the loss function of the NNPU learning for the binary classification problem. It contains two parts. The first one is empirical risk of the positive samples evaluated with the positive labels. And the second is a mixture of the empirical risk of the positive samples and the unlabeled samples evaluated with the negative labels. And its empirical risks are defined based on the sample-wise loss function. This method was found theoretically and empirically better and more robust to overfitting. So what we try to do is to extend this NNPU learning paradigm to our defined logistic PARAFAC2. First, we try to replace those sample loss function with the pointwise loss of our logistic PARAFAC2. Here, each sample is one entry of our irregular tensor, which leads to the final objective function by combining all those empirical loss together, we have this final objective function. So besides, we also have several regularizations for the better interpretability. The first one is the uniqueness regularization. So in the ordinary PARAFAC2, we have a factor invariance constraint. Basically, this UK transpose UK is a constant. This ensures the uniqueness of the PARAFAC2. And we propose a regularization term by treating this phi as also a variable. So we try to minimize the deviation of this UK transpose UK and this phi. This regularization is easier to be solved than the hard constraint. And we also propose a time-aware temporal smoothing regularization. Here the UKT is a temporal factor of the subject k at time t, and this UKT minus 1 is the temporal factor of the subject k at time t minus 1. Here the idea is to penalize the deviation between two consecutive time steps. That means we believe if two points are closer in time, they should be closer in their latent factors. And this delta I is Ti minus Ti minus 1, which means which represents the time gap between two temporal steps. For example, in the AHR context is the two hospital visits. So this means we impose stronger regularization if two steps are closer in time. So in this way, we discover the smooth temporal factors which can be more interpretable. So putting all this together, we can define our optimization problem as this, basically by stacking the loss function and also the two regularizations. And we also have the negative constraints for better interpretation, and we also have the infinite norm constraint to ensure that this UK, SK, and V are not too spiky. We adopt the alternating update and alternate between this UK, SK, and V to solve for those parameters. We use Atom Optimizer and compute the gradient by backpropagation on the fly. So we evaluate our model in three datasets. The first one is Sutter, which is collected from Sutter Health, a very large US-based health provider network. We use diagnosis and medications of each clinical visit of the patients. The second dataset is a publicly available CMS dataset. We use the diagnosis of each clinical visit of the patients. And the third one is Mimic3, which is a very large-scale ICU dataset. We use the medications and abnormal lab tests. And we evaluate against four baselines. The first one is COPA, which is a SOTA PARAFAC2 factorization model. The second is Spartan, is another PARAFAC2 model for sparse data specifically. And the third one is PUMC. This is the binary matrix completion model based on the PU learning. And another one is one-class matrix factorization, which handles the binary matrix completion based on the sampling method. So here shows some statistics of the three datasets. To perform the evaluation, we first extract 10% positive entrants for validation and parameter tuning, and hold out 20% of the positive entrants for test. Then we randomly match 10 negative entrants with value of zeros in their raw data for each positive test entrance, and then together with the of the 20% held out positive entrants together at the test set. Finally, we use the remaining 70% of the positive entrants as the training set. We use the PRAUC as evaluation metric because the binary and imbalanced nature of the dataset. So first, we measure the completion performance with the varying ranks. We vary the rank of the models from 10 to 300. And this figure shows the performance of our model and all the baselines in three different datasets. This blue line, dotted line are our models, and we can see that LogPar consistently outperforms all baselines for all target ranks. And the performance of this PUMC decreases with increasing rank, which indicates that it suffers from severe overfitting with increasing target ranks. Then we fix the rank of all models to 30 and measure the completion performance with varying missing ratios. And again, this blue line is our model. And here we can see a larger gap between our model and all the baselines, which indicates that LogPar consistently outperforms all baselines for all levels of missingness. And with the increasing level of missingness, our model is more robust. We also performed several downstream prediction tasks. We first fixed the missing ratio to 30% and split the patients into training set and test set. So we first train LogPar with the training set to learn the latent vector factor V, and then we project the test set, the test patients onto the learned factor V. And then we use this diagonal SK as features and train a logistic regression for classification. We use fivefold cross-validation. So this is the heart failure prediction task on the Sutter dataset, and this shows the PRAUC for the mortality prediction on the MIMIC3 datasets. And it's clearly that LogPar outperforms the two PARAFAC2 factorization baselines, the COPA and Spartan. The reason is that our model considers the missingness, which helps the downstream prediction tasks by a large margin. Finally, we perform an ablation study. We use the Sutter dataset and we set the missing ratio to 30% and measure the completion performance. We also performed an ablation study. We used the Sutter dataset and set the missing ratio to 30% and measure the completion performance. Here, the PN represents positive negative loss, which means we don't consider any missing data. Here, this U and I dot means the uniqueness regularization, and this means the smoothness regularization. So first, if we compare row number 2 and row number 3, we can observe significant improvement by incorporating the PU learning. And if we compare the row number 4 and row number 3, we can observe that uniqueness regularization is essentially important for PARAFAC2 model because we observe significant improvement for all number of ranks. And if we compare row number 3 and row number 5, we can see that the temporal smoothness regularization further helps the completion, especially when the rank is low. Finally, we perform a case study where we interpret the phenotypes. We used the Sutter data set and set the missing ratio to 30%, and the weighting here after each phenotype is the logistic regression weighting for the heart failure onset prediction. And we can see that the first two phenotypes are two phenotypes with the highest weight, and both are very relevant to the heart failure. And the other phenotype contains ear, sense organ, and upper respiratory disease, which is irrelevant to heart failure. So this means the factors learned by our model are also interpretable. So to conclude, we propose LogPar for binary irregular tensor factorization with explicit consideration of one-class missingness. And LogPar is the first PARAFAC2 model considering the missingness, and we incorporated the PU learning, which greatly helps the completion. We proposed the uniqueness and temporal smoothness regularization for the PARAFAC2 factorization model. And the empirical evaluation validates the effectiveness of LogPar and its components. That's all. Thank you for your listening. If you are interested, please check out our paper for more details. Thank you.